Welcome to this lecture on the model matrix in estimation. If you have ever wondered how computers can predict outcomes from massive amounts of data in a fraction of a second, you are in the right place. Today, we will uncover the mathematical engine that makes modern data analysis possible. We will build this concept from the ground up, ensuring you understand exactly how it works. Let us start by understanding what a model matrix actually is. Imagine you are trying to predict a car's fuel efficiency based on its weight and engine size. If you have data for 50 cars, writing 50 separate equations by hand is exhausting. Instead, we use a model matrix. Think of it as a perfectly organized digital spreadsheet. Every row is a specific car, and every column is a feature. By packing all this data into a single grid, we can use the rules of matrix algebra to solve for our predictions in one swift motion. This is why it is so powerful. Now that we understand the idea, let us look at the formal definition. In linear regression, the model matrix is usually denoted by the capital letter X. It has n rows, where n is the total number of observations we collected. It also has p columns, representing the number of parameters we want to estimate. Crucially, this includes one column for each predictor, plus an extra column made entirely of ones. Why ones? Because this column allows us to calculate the y-intercept, which is our baseline prediction when all other inputs are zero. Let us visualize this structure to make it concrete. Here, you see the model matrix X. Notice how the rows correspond to each observation, from 1 down to n. The columns represent our predictors. The very first column is the intercept column, filled entirely with ones. The subsequent columns hold the actual data values for each predictor, like weight or engine size. This grid transforms a messy real-world problem into a clean, solvable mathematical format. Before we jump into matrices, let us see where they come from conceptually. For a single observation, we write the relationship as a simple sum. Here, y sub I is the actual observed outcome, like the fuel efficiency of one specific car. Beta 0 is the y-intercept, representing our baseline value. The other beta symbols are the unknown coefficients we want to find. They tell us exactly how much each predictor matters. The x values are our actual input measurements. Finally, epsilon sub I is the error term, representing the random noise or the difference between our perfect model and the messy real world. Writing out that long equation for every single data point is tedious, so we stack them all on top of each other to form matrices. This beautifully simple equation is the exact same thing, just written in matrix form. Y is a tall single-column vector containing all our observed outcomes. X is our model matrix, containing the column of ones and all our predictor data. Beta is a vector containing all the unknown coefficients we want to discover, and epsilon is a vector of all the error terms. Our goal is to find the best values for beta. To find the best values for beta, we use the method of least squares, which minimizes the sum of the squared errors. This leads us to the normal equations, and ultimately to this final most important formula. Beta hat is our estimated vector of coefficients, our best calculated guess. X transpose simply means we flipped the model matrix's rows and columns. Multiplying X transpose by X creates a square summary matrix. We then take its inverse and multiply it by X transpose Y. This perfectly calculates the exact weights that minimize our prediction errors. Let us walk through a simple numerical example to see exactly how this works in practice. Suppose we want to predict a student's test score based on the number of hours they studied. We have data for 3 students. The first studied 1 hour and scored 2 points. The second studied 2 hours for 4 points. And the third studied 3 hours for 5 points. First, we construct the y vector, simply by listing the 3 test scores vertically. Then we build the X matrix. The first column is entirely ones for the intercept, and the second column contains the actual hours studied. Continuing with our calculation, the next step is to find the transpose of x. We do this by flipping the rows into columns, giving us a matrix with 2 rows and 3 columns. Now, we must multiply x transpose by the original x matrix to find our square summary matrix. By performing matrix multiplication, we get a 2 by 2 matrix. The top left number 3 is simply the number of data points. The other numbers represent sums of the x values and sums of the squared x values. Next, we need to calculate the right side of our normal equations, which is x transpose multiplied by y. This multiplication gives us a new vector with 2 values, 11 and 25. Now we have all the pieces, but we still need the inverse of our x transpose x matrix. For a 2 by 2 matrix, we swap the diagonal elements, change the signs of the off-diagonal elements, and divide by the determinant. The determinant is 3 times 14 minus 6 times 6, which equals 6. We divide our rearranged matrix by 6 to get the true inverse. Finally, we multiply this inverse matrix by our x transpose y vector to find our estimated coefficients, beta hat. After performing the multiplication and dividing by 6, we get our final answer. The top value, 0.67, is our estimated y-intercept. The bottom value, 1.5, is our estimated slope. Physically, this tells us that a student who studies 0 hours is expected to get about 0.67 points. And for every additional hour they study, their score increases by 1.5 points. Our formula relies on a massive hidden assumption that the inverse matrix actually exists. A critical failure occurs if the matrix is singular, meaning it cannot be inverted. Think of it like trying to divide by 0. The math simply breaks down. This usually happens due to perfect multicollinearity, where 2 or more columns contain the exact same information, just disguised differently. It can also happen if you have more unknown parameters than actual data points. When the matrix is singular, its determinant is exactly 0, and the formula completely fails. Let us look at a scenario where the math breaks down to understand singularity practically. Suppose we are predicting a person's running speed. We record their leg length in meters as our first predictor and their leg length in centimeters as our second predictor. We have data for 2 runners. We build the X matrix using a column of ones for the intercept, a column for meters, and a column for centimeters. Notice that since 1 meter is exactly 100 centimeters, the third column is just the second column multiplied by 100. Now, let us calculate the transpose multiplied by the original matrix. We compute the 3 by 3 summary matrix. To find the coefficients, we would normally need to invert this matrix. The first step of finding an inverse is calculating the determinant. Look closely at the numbers in our summary matrix. Because the third column in our original data was perfectly predictable from the second column, the third row of this new matrix is simply the second row multiplied by 100. If you calculate the determinant of this specific matrix, you will find that it is exactly 0. Because the determinant is 0, the inverse matrix does not exist and the math has completely halted. This perfectly illustrates the danger of perfect multicollinearity. The model cannot decide whether to assign the predictive weight to the meters column or the centimeters column because they provide the exact same information. To fix this, we would simply delete the redundant centimeters column and run the calculation again. Let us review the key takeaways. The model matrix is the fundamental bridge between raw data and linear estimation. By organizing all our observations and predictor variables into a single grid, we can use the power of matrix algebra to solve complex regression problems instantly. However, remember that the core formula relies on the matrix being invertible, which requires our data to be free of perfect redundancies. Understanding how to build and manipulate this matrix is your first crucial step in mastering modern statistical modeling.